Good morning, students. Welcome to 12th standard physics class. Students, today's topic is on atom models, unit 9. The first topic is Rutherford's model. In this experiment, a source of alpha particles is kept inside a thick lead box with a fine hole. The alpha particles coming through the fine hole of lead box pass through another fine hole made on the lead screen. These particles are now allowed to fall on the thin gold foil, and it's observed that the alpha particles passing through gold foil are scattered through different angles. A movable screen which is made up of zinc sulfide is kept on the other side of the gold foil to collect the scattered alpha particles. Whenever alpha particles strike the screen, a flash of light is observed which can be seen through a microscope. Results of this experiment are sum of went straight, sum of rays deflected through a small angle, sum of deflected through the angle more than 90 degree. This is called alpha scattering experiment. Next, postulates of Bohr atom model. The electron in an atom moves around nucleus in circular orbits under the influence of Coulomb electrostatic force of attraction. Electrons in an atom revolve around the nucleus only in certain discrete orbits called stationary orbits. And electrons in such orbits do not radiate electromagnetic energy. Only those discrete orbits allowed are stable orbits. According to quantum mechanics, particles like electrons have dual nature. The standing wave pattern of the de Vries wave associated with orbiting electron in a stable orbit. The next, radius of the orbit of the electron and velocity of the electron. Consider an atom which contains the nucleus at rest and an electron revolving around the nucleus in a circular orbit of radius Rn. Nucleus is made up of protons and neutrons. Proton is positively charged and neutron is electrical neutral. The charge of nucleus is entirely due to the charge of protons. Z be the atomic number of the atom. Then plus Ze is the charge of the nucleus. Minus E be the charge of electron. From Coulomb's law, the force of attraction between the nucleus and the electron is Rn is equal to 4 pi epsilon naught m Vn Rn whole squared by Z me. The final value is Vn is equal to the velocity is equal to h by 2 pi ma naught Z by n. Excitation energy and excitation potential. The energy required to excite an electron from lower energy state to any higher energy state is known as excitation energy. Excitation potential is defined as excitation energy per unit charge. Ionization energy and ionization potential. The minimum energy required to remove an electron from an atom in the ground state is known as binding energy or ionization energy. The amount of energy required to remove an electron from the ground state of an atom is known as first ionization energy. Then ionization potential is defined as ionization energy per unit charge. Next, atomic spectra. The materials in the solid, liquid and gaseous status emit electromagnetic radiation when they are heated up, and this emitted radiations usually exhibit continuous spectrum. For example, when white light is examined through a spectrometer, electromagnetic radiation of all wavelengths are observed, which is continuous spectrum. This is called spectra. Hydrogen spectrum. When the hydrogen gas enclosed in a tube is heated up, it emits electromagnetic radiations of certain sharply defined characteristic wavelength called hydrogen emission spectrum. When any gas is heated up, the thermal energy is supplied to excite the electrons. Similarly, By all occurring light on the atoms, electrons can be excited. Once the electrons get sufficient energy as given by Bohr's postulate, it absorbs energy with particular wavelength and jumps from one stationary state to another state with those wavelengths for the colors that are not observed are seen as dark lines in the absorption spectrum. The first figure is emission spectrum of hydrogen in wavelength. Second one, absorption spectrum of hydrogen in wavelength. That's all. The wavelengths of these lines can be calculated with great precision. Further, the emitted radiations contains wavelength both lesser and greater than wavelength of lines in the visible spectrum. Notice that in each series, the distance of separation between the consecutive wavelength decreases from higher wavelength to the lower wavelength, and also wavelength in each series approach a limiting value known as the series limit. These series are named as Lyman series, Balmer series, Paschen series, Brackett series, P1 series. First one, element series. For n is equal to 1 and m is equal to 2, 3, 4 like this. In equation, the wavelength of spectral line of Lyman series which lies in ultraviolet region. The next one, Balmer series. For n is equal to 2 and m is equal to 3, 4, 5. In equation, the wave numbers or wavelength of spectral lines of Balmer series which lies in visible region. Next, Paschen series. Put n is equal to 3 and m is equal to 4, 5, 6. These are continuous numbers. In equation, the wave number or wavelength of spectral lines of Paschen series which lies in infrared region. Okay, next one, Brackett series. N is equal to 4, m is equal to 5, 6, 7. The wave number or wavelength of spectral lines of Brackett series which lies in infrared region. Then last one, P1 series. For n is equal to 5 and m is equal to 6, 7, 8. The wave numbers or wavelength of spectral lines of P1 series which lies in infrared region. Next, atomic and nuclear masses. One atomic mass unit is defined as the 1/12th of the mass of the isotope of carbon. Next, size and density of the nucleus. The alpha particle scattering experiment and many other measurements using different methods have been carried out on the nuclei of various atoms. The nuclei of atoms are found to be approximately spherical in shape. It's experimentally found the radius of nuclei for Z is greater than 10 satisfies the following empirical formula. R is equal to R naught A power 1 by 3. Here A is the mass number of the nucleus and the constant R naught is equal to 1.2 F. Next, binding energy curve. The average binding energy per nucleon is the energy required to separate single nucleon from the particular nucleus. Alpha decay. When unstable nuclei decay by emitting an alpha particle, it loses 2 protons and 2 neutrons. As a result, its atomic number Z decreases by 2. The mass number decreases by 4. The equation XZA gives ZA minus 4 Z minus 2Y plus helium mass number 4 atomic number 2. Here X is called the parent nucleus and Y is called the daughter nucleus. For example, decay of uranium. Next, beta decay. In beta decay, a radioactive nucleus emits either electron or positron. If electron emitted, it is called beta decay, and if positron is emitted, it is called beta plus decay. The positron is an antiparticle of an electron whose mass is same as that of electron and charge is opposite to the electron, that is plus E. In beta decay, the atomic number of the nucleus increases by 1. but Morse number remains the same. This decay is represented by x z power a gives z plus 1 y power a plus e minus. The next, gamma decay. In alpha and beta decay, the daughter nucleus is in the excited state most of the time. The typical lifetime of excited state is approximately 10 power minus 11 seconds. So, this excited state nucleus immediately returns to the ground state or lower energy state by emitting highly energetic photons called gamma rays. The gamma decay is given by x base z power a gives x z a plus gamma rays. Half-life. We can define the half-life T 1 bar 2 as the time required for the number of atoms initially present to reduce to 1/2 of the initial amount. This is called half-life. So, n is equal to 1 by 2 n naught. It is called half-life. The mean lifetime of the nucleus is the ratio of sum or integration of lifetimes of all nuclei to the total number nuclei present initially. Carbon dating. The important use of beta decay is radioactive dating or carbon dating. Using this technique, the age of an ancient object can be calculated. All living organisms absorb carbon dioxide from air to synthesize organic molecules. In this absorbed CO2, the major part is carbon 612 and very small fraction is radioactive, whose half-life is 5730 years. Nuclear fission. The process of breaking of the nucleus of a heavier atom into two smaller nuclei with the release of a large amount of energy is called nuclear fission. Nuclear fission means அணுக்கரு பிளவு. So this reaction is called chain reaction. The atom bomb is an example of nuclear fission. Nuclear fission. When two or more light nuclei combine to form a heavier nucleus, then it is called nuclear fission. So sun is powered by proton-proton cycle of fission reaction. Next, the inner parts of nucleons. According to quark model, proton is made up of two up quarks and one down quark, and neutron is made up of one up quark and two down quarks. Here quark means very small particles. Okay students, today's topic is over. Today's homework. Students, I have given homework from this topic. Read the questions and answers well and then write in your fair note. Thank you students. God bless you all.